Okay, so first, let's do a quick recap on the. So for today's lecture, I'm planning to more of a going over some moment-generated function that is related to homework 3, and then we will move to another regime where we can talk about data and then using what we have learned to apply the methods to calculate some probability of some as an application. So that will be for today's schedule. Okay, so as a quick recap, maybe let's start with the moment-generated function. So, yep. And we are going to use the uniqueness theorem to identify the distribution. Okay, so I'm going to basically repeat some of the material from the end of the last lecture, and also provide a few examples. And then after that, we will proceed to the application parts on calculating some probability of some. Okay, so for example, here, let's denote a random variable x that follow a Poisson distribution with parameter lambda 1, and let y be another random variable that follow another Poisson distribution with parameter lambda 2. And then we have the independence assumption. So here, I write x like with a perpendicular sign, and then another variable y. This is saying x and y are independent. And then with this assumption, then you are able to use some properties that we introduced on the moment-generated function to discuss in this case, the sum of the two random variables. So here we are interested in the distribution of the sum of x and y. Okay, and because they are independent, so we know the moment-generated function of the sum is equal to the product of the two. Okay, so this is using the property 1. Because they are independent, so the moment-generated function of the sum is equal to the product of the individual moment-generated function. Okay, and then if you look up your notes or your cheat sheet, you have write down. So this is something you have write down on your cheat sheet during the midterm 1. So the moment-generated function for a Poisson distribution is the e raised to the power of the parameter, and then et minus 1. Or this is something that you also, probably I asked this during the lecture, during the midterm. So this should be the solution to your midterm problem. Okay, and then you will also have because the other parameter, the other variables is also a Poisson random variable. So you will also have the same formulation, except that you have a new parameter lambda 2. Okay, so what we did here, just plug in the moment-generated function to the corresponding random variable x and y. Okay, so each of them is the moment-generated function for a Poisson, and right now we just plug in the Poisson moment-generated function, and then with the corresponding parameter. So the parameter for the x has a lambda 1, and the parameter for the y has a lambda 2. So we just plug in the parameters and then write down the corresponding formulas. And then we can group the things in the following way. So we have the lambda 1 plus lambda 2 multiplied by the shared term. Okay, so this is because E of A multiplied by E of B is equal to E of A plus B. Okay, and then the A is the lambda 1, and then et minus 1. The B is the lambda 2, et minus 1. And then because they share the same factor, e raised to the power of t minus 1, you can just bring that on the right-hand side, and then you have the lambda 1 plus lambda 2. Okay, and this is also, I think this is an example from last week, and then we mentioned that by looking at this expression, you will notice that it looks the same. I mean, the structure looks the same as the Poisson moment-generating function. So, for example, that is the formula for the moment-generating function of a Poisson random variable. And then by looking at these two, in terms of the structure, they look very similar, except that you have a different value for the lambda. So then we can claim that the distribution of x plus y also following a Poisson distribution, but with a new parameter, which is lambda 1 plus lambda 2. Okay. So this is due to the uniqueness theorem. If you can recognize the formula of the moment-generating function, that you can claim that the distribution of the new random variable follow the known distribution. In our case, it's the Poisson distribution. Any question up to this point?
So in addition to knowing the probability mass or density functions of a given distribution, we need to know their moment generating function before each distribution?
Yes, so to recognize the distribution, you will need to use the moment generating function, and that is due to the uniqueness theorems. So if you just play around with the random variables, you might have a good knowledge of what is their expectation, their variance, or those kind of things. But to claim what the underlying distribution is, it has to go through the moment generating function. So the moment generating function is kind of like a magnifier. You when you look through the magnifier and then see its true to identify its true identity, and that can only be done through the moment generating function. And also last time we have one example is that when we have n of the exponential distribution, when we calculate the moment generating function, their sum is the gamma distribution. So playing around with the random variables, or when you summing up your samples, it does not tell you what is the underlying distribution. So you are not able to calculate, like perform analysis, like calculating the probability of some downstream task. But to recognizing the distribution, everything need to go through the moment generating function. It's like an identifier. Yeah.
Can you remind us what the uniqueness theorem says?
Yeah. So basically just saying if your let me see if that I can. Okay, so if the moment generating function of some y has the same, let me just call formula then. With the moment generating function of x, then x and y have the same distribution. But one common here is that the parameter may be different. And it will depending on the result. Something like that. Yeah. So what we have used is what we have done here. So we know that x and y, they each follow a Poisson. So that's what we know of. And then we also know their moment generating function. That's what we did throughout the lecture before midterm 1. So we know their moment generating function. And once we calculating the moment generating function of the sum, we get the result. And then it shares the same formula as the moment generating function of the Poisson. And then we can claim that the sum of x and y also following a Poisson distribution. But the parameter could be slightly different. So in our case, by reading from the resulting moment generation function, we know that the parameter of that new distribution is lambda 1 plus lambda 2. Yeah, so that is what the uniqueness theorem is used to identify the true identity of the moment generation function. So the sum of some random variables may not be as the same as the individual. And one example that we have seen last time is the exponential distribution. Yeah. And there are lots of other random variables. When you sum them together or you scale and then shift the parameters, when you shift the random variables, they might not end up with the known distribution. You will need to use the moment generation function to recognize, to identify what is the underlying distribution. Yeah.
Just to clarify, the uniqueness theorem doesn't apply to all distributions?
Yes. Yeah. So a conceptual idea is that the moments you will have the first moment, the second moment, the third moment, and then you can keep going to a relatively large moment. So moment generation function is a construct that can calculating all these moments. By taking the kth order derivative, set t equals 0, you can get each of the each of the moments. Okay. So if you have a random variable that you know that has the moment generation function, basically is that defining all the moments for that random variables. And now you have the new random variables. If you can recognize, if you see that the moment generation function for the new variables have the same formula, have this in terms of the moment generation function, that is essentially saying the moments for your new, so this is known, if you know about some information or all the moments for x. And now this is a new random variable. So if you are able to match all the moments for that new random variable, then what you are saying is that essentially they share the same distribution. So that is the idea of using moment generation function to recognize the distribution. They share the same distribution. So that is the underlying reason to claim that if you know the moment generation function for y, and then if it looks the same as the moment generation function of the x, then you are essentially matching all the moments for the new random variable, then the new random variable also should share the same distribution. So that is the underlying idea for the uniqueness theorems. Yeah. So essentially just matching all the moments, but moments can be generating from the moment generation function. The name is that a function that generates in the moment. So if they have the same moment generation function, then they essentially share the same all k moments, and then they share the same distribution. So that is the underlying idea of using moment generation function to recognize or to identify the distribution. Yeah. And most of the time, you just need to use the first and the second moment to calculate the expectation and the variance. Those are the two most important statistical quantities. But if you're able to match all the kth moment, then you just basically replicating the shape of the y and or discover the shape of the y, and then you're recognizing the shape of the y or the random behavior or the random phenomenon has the same as the known variable x, then they essentially have the same distribution. So that's the idea. Okay, so yeah, any other question or comments? Okay, next I'm going to talk about the normal case. I think we also showed, so I'll just repeat what the examples from last time. Okay, so here, let's work with the normal distribution. And then we have x following a normal distribution with mu1 and sigma 1 squared. And then we also have another variables that follow a normal with mean mu2 and then the sigma 2 squared. Okay, and also x and y are independent. Okay, so now my question is, find the distribution of x plus y. Okay. So again, so here our goal is to recognize what is the distribution of x and y, and also calculating or provided the parameter for this new distribution. Okay, so for this kind of problem, start with the moment general function. So we want the moment general function of x and y, and then we want to see what is the result, and then we will compare with the result with some known moment general function, and then we can recognize what is the distribution of the sum from there. Okay, so we are interested in the moment general function of the sum of x plus y. Because they are independent, you will have the moment general function of x itself multiplying by the moment general function of y. Okay, that is from the property 1 that we introduced. Because they are independent, so the sum is equal to the product of the moment general function. Okay. Last time we also write down that the moment general function for the normal is t multiplied by the mu plus 1/2 t squared sigma. And here we plug in the corresponding parameter, which is mu1 and sigma 1. Okay, so that is the moment general function that we derived from last time. And then multiplying by the same copy, but with the new parameter mu2 and sigma 2. Okay, so here we just plug in the formula. And then with the corresponding parameter for x and y. And then what we did last time is grouping the things in the following way. So t times mu1 plus mu2 plus 1/2 t squared sigma 1 squared plus sigma 2 squared. Okay, so that is the resulting moment general function for the sum. And then now we can see that the resulting formula of this sum is, in terms of the structure, is the same as the moment general function for a normal distribution. So we can claim that the sum of the two normal, where individually they follow normal, but now the sum also following the normal distribution. So we using the uniqueness theorems to identify the distribution. So we can claim that the sum following a normal. And now we just need to read from the formula what is the new parameter mu, the mean, and what is the new variance. Okay, so now by matching the moment general function, we can recognizing that the new mean for this sum is mu1 plus mu2. And then the variance is sigma 1 plus sigma 2. Okay, so this is from reading from these new results. Okay, so the distribution here is recognized by the uniqueness theorem. And then here, by comparing to the formula, you can recognizing what is the new mean and the new variance here. Okay. Let me see what example we did last time. Yeah, I think this is the same example we did. And yeah, and also this is the example where we have a sequence of a exponential distribution, but in the end, we end up with a gamma distribution. So don't take it for granted that if individual random variable follow like a distribution A, then their sum or their variation also following the same. So don't take it for granted. You always need to use the moment function to check if you perform some transformation of the moment function of the random variable. So again, here individually, each of them follow an exponential distribution, but when we're talking about the sum, they follow a gamma distribution. So when you perform analysis for a group, so for example, each of them can be a patient or can be a samples from the data that you collect or a measurement that you collect. So if you want to perform some analysis on the sum or even the average of your patient data that you collect, make sure you double check what is the result or the new distribution. It might not be the same as the individual distribution. So this is saying individually, they might behave like an exponential distribution. But when you aggregate them together or when you take the average of the patient or when you perform some transformation of your patient measurements, they may not be the same or they may not behave the same as what individual behave. So when you perform some manipulations on or transformation on your data set or your individual things that have some random behavior, make sure you check what is the underlying or what is the new random behavior. So in this example, they are not the same. So don't take it for granted that how individual behave when you consider it as their sum or their total variations, then they share the same, which is not true. So always use the moment function to double check. Okay, so yeah, we did the normal, we also did this example. So maybe let me provide two more examples that is more related to the homework, just in case you need more hint on the homework. Okay. So yeah, before we start, any other question or comments? Okay, so our next example is that we have, instead of two normals, we have n normal random variables. So here we have n random variable, and then here we write IID normal with mean mu and then the sigma square. So IID here again stands for independent and then identically distributed. So this is a very important assumption when you perform your analysis. So in many of your analysis, you are making this assumption that each of your patients or the data that you collect are independent and identical distribution. That is a very good assumptions, but it might not be true. But when people performing analysis, for example, when you having a control group or a treatment group to your patient or to some cells, you are essentially making the assumption that each of the individual cell or patients are independent from each other, and then they share the same distribution. Yeah. So that is one assumption that many people, when they perform analysis, the assumption that they make. Okay. So IID. Okay. So now the question here is that what is the distribution of their sum? So here let's denote T is the sum of x1 plus x2 all the way to xn. Okay, so we know that your individual patient or your individual measurement following a normal behavior that is centered around the mean, and then it has a lower probability when it's too far away from the mean. Okay, so their individual random behavior look like that. But now the question is, when you group everything together, what is their random behavior? And then we will need to go through the moment function to check what is the the random behavior of that sum, which is the t here. Okay. So here we are interested in the moment generating function of the new random variable t, which is x1 plus x2 plus all the way to xn. Okay. So if we're able to recognize the moment generating function for this sum, then we can claim the distribution for the new random variable t. Okay, and let's see what will be the resulting random variable moment generating function. Okay, by property 1, we know that the sum of the moment generating function of sum is the product of the individual moment generating function. So we'll have the moment generating function of x1 multiply by the moment generating function of x2 multiply all the way to the moment generating function of xn. Okay. And this is due to independent. So we are using the first I from the IID. Okay. So lots of the calculation is valid only under the assumption that you make. So this is the assumption, and then because they are independent, so we're using the first I here. Because they are independent, you can write the moment generating function of the sum is the product of the individual moment generating function. Okay, next, it just plug in the moment generating function that we derived from last time. Okay, so we will have e raised to the power of t mu plus 1/2 t squared and sigma squared. That is for the first one, because each of the random variable xi follow the normal distribution with mean, mu, and sigma square, so their individual moment generating function take the form what we derived from last time. Okay, so that's for x1. We also need to write down the 1 for the x2. And then keep multiplying all the way to the last one. Okay, so each of them follow the normal distribution with the mean and the mean mu and the sigma square. So that means the moment generating function for each of them take the same form. So this is the part that you're using the ID, the second I and the last D, the ID part, the identically distributed. So because each of them, they are identically following the normal, so they all have the same formula, the mu and the sigma square. So in the previous example here, they have different mu and different sigma. So this is not identically distributed. Identically distributed. Okay, because they have different mu and different sigma. But in the second example here, they are identically distributed because they all have the same normal with the same mean and the sigma square. So they are identically distributed, and then they are also independent, so they are IID. Okay, now we just need to group the products in the following way. So here again, E of A multiplied by E of B is equal to E of A plus B. So essentially you will have the exponential raised to the power of their A. If you call the power for this one is A, this one is B, and this one is the C, and all the way to the last one, you just sum all the powers together, then you will end up with the following expression for the powers. So you will have n copies of the t multiplied by mu plus 1/2 t squared and then sigma squared. Because they are all identically distributed and then there are n copies of them. So when you take the sum of A plus B, so essentially there are A plus A plus A plus A, and then there are n copies of them, so you have n multiplied by the power, so n multiplied by that. Okay. But this is not enough, not yet, that allows us to recognize the distribution. So let's write one more step, is that we have the t multiplied by n multiplied by mu plus 1/2 t squared, and then n multiplied by sigma squared. Okay. So by looking at this formula, now we can recognizing that the sum of the n individual normal random variable also follows the normal distribution because it shares the same formula here. The only difference is that we have a new mean and a new variance. Okay, so now we can claim that the x1 plus x2 plus all the way to xn following a normal. Okay, so again, this is identified by the uniqueness theorem. And then the mean is n multiplied by mu. So you can read it from your resulting formula here. Okay, so that's your new mean. And then the variance is n multiplied by sigma square. So again, also reading from here. So this example is showing that if your individual measurement following a normal distribution, then their sum here also follow a normal distribution. Yeah. So some of the examples is that their resulting sum or their average share the same distribution of the individual behavior, but some of them might not. So just don't take it for granted. Make sure you double check what is the resulting or the underlying distribution for your for transformation of your data. Any question or comments? Okay, let's do one more example. So now again, so let's do a follow-up question. Find the distribution. So again, we have the x1 to xn, each of them following a normal. Now the question is find the distribution of their average. Okay, so here let's call it x bar, and x bar is defined as the average. So the sum from 1 to n and then xi, okay, where xi following the normal with mean mu and then the sigma square. So again, we have n of the variables, each of them following a normal distribution. So the previous example is that we noticed that, or we identified that the sum of the n normal random variable following a normal. So the second or the follow-up question here is that what is the distribution for that average? So this is a new transformation of a measurement. So very often we are interested in the mean of your 100 measurements. So this is one example where we are trying to find out what is the distribution for the average. So we call it x bar, which is 1 over n, and then when multiplied by the sum of all your measurements. So you have n measurements, like for example, like n student heights, but you are interested in the random behavior of the average here. So you can have like one average from these 100 students. You can also have another sample, another 100 measurements from another set, 100 students. So now you're interested in what is the behavior if you take the samples, the average, and you can take different samples of 100 people. We are interested in what is the random behavior of that average. And let's see what is the underlying distribution. Okay. So here we are interested, or we want to start with the homogeneous function of the x bar. Okay. And then the x bar is just the 1 over n multiplied by t. Okay, so t is defined as the sum. Okay, so the average x bar is 1 over n multiplied by the sum. And here, I'm just going to write the x bar equal to 1 over n multiplied by t. Okay. And now we can use the other properties. I think it's the property 3. Is that when you scale a random variables, this is equal to the moment general function for t, but you also scale the input of this function by that factor. So here, okay, so maybe let me bring back what we have from the formula. Okay, so last lecture, we have this formula. This is the property 3. We mentioned that if we scale a random variable by a factor of b, this is essentially the same as you have the moment general function for the random variable x, but you scale the input of this function by the factor of b. Okay, so in our example is that the b here is a particular number 1 over n, the factor that you take the average by dividing by your n sample size. Okay, so in our case, the b here, the formula b is we should plug in 1 over n. Okay, and then when we apply the property 3, we notice that we can just use the moment general function for the original random variable, but we scale the input by a factor of b. In our case, b is 1 over n. Okay, so that is what I put down here. I'm using the property 3 by bringing the factor that we scale to the random variable into the input of that moment general function. So we scale the input of t by a factor of b, and b here is the 1 over n. Okay. And now we can just use the result that we derived from above. So in the previous example here, we derived that the moment general function for the t takes this particular form. So we can directly or reuse the formula that we derived from here. Okay. So now we are going to reuse the result from above. Okay. So the moment general function for t takes this form. So this is the moment general function of the sum. Okay. But now we have a factor of 1 over n to take care of. So this is saying we will have, so the t become the new input. So we have the t over n. So that is the new input for that moment general function, the t over n. And then reading the new mean from here. So this is n multiplied by mu. And that is the mean for the random variable t. Okay. Plus, let's continue from reading from the previous result. So t squared. Okay. So whenever you see a t, you need to replace by the new input. So the new input is t over n, and then taking the square. And then there's a 1/2. Okay, and then the variance for the random variable t is n multiplied by sigma squared. So bring in n multiplied by sigma squared. Okay, so that is the moment general function for the average or the x bar. Now let's further simplify that. You will have the e raised to the power of t multiplied by mu plus 1/2 t squared 1 over n squared multiplied by n multiplied by sigma squared. And further simplify into the following result. So t multiplied by mu plus 1/2 t squared sigma squared over n. Okay, so that is the moment general function for the average x bar. And again, we can recognize that it shares the same formula with the moment general function of a normal random variable. So we can claim that the x bar also following a normal distribution. So again, this part is recognizing through the uniqueness theorems. Now the question is, what is the new mean and the variance? So the mean, by reading from this formula, we know that the mean is mu. Okay, and then the variance, by reading from the second term, is the sigma square over n. Okay, so when you work with normal random variables, if you assume that your measurements coming from a normal distribution, the sum and also the average will also have the same random behavior as the normal distribution. But here, the only difference is that their mean and the variance are slightly different. So we can also make a quick summary for our the result that we derive here. So if individual xi following a normal with mean mu and sigma square, and then if you assume that all of your data or all of your measurements, they all follow the same normal distribution, then you will have the x bar also following a normal with the mean mu, but the variance has been scaled by the number of samples that you collected. So if you collected 100 samples or 100 measurements, then the variance will be shrinked by a factor of 1 over n. Okay, and our previous result is that the sum, if you're interested in the sum of all the sample that you collected, then they all will also behave like a normal random variable, but their new mean is that you have to scale the mu, the average, by a factor of n, and then also their variance by a factor of n. So this is what the result is saying. Well, the examples, and then you can consider them as a result. So for normal random variable, when you perform some transformation, then they still follow the normal. Yeah. But we have also seen one example is that the individual follow exponential, the sum will follow a gamma. Yeah. But one thing is that actually the exponential distribution is just a special case of gamma. So many of the things are just a special case of gamma. So gamma is a very general formula. So you have a very complex probability density function. But exponential and also there are other distribution, other random variables, they are just some special case of a gamma distribution. Yeah. So if you take the sum of the gamma, that indeed follow gamma, because the sum of the exponential follow gamma. And the exponential is a special case of a gamma distribution. And gamma is a very general distribution to work with. Any question or comments here? I think this provides more information on the homework.
Question. When
Yeah.
working with X bar specifically, are we supposed to have already done the case of the X in the identical distribution beforehand and know what the mean and variance are supposed to be?
So that is all coming from your assumption. So for your analysis, as a researcher, you will assume that each of the measurements or the data that you collected following a normal. And then you will need to provide the mean and the variance to facilitate the downstream calculation. So now the question would be, what is the so one potential problem is a question that a researcher can ask is that what is the probability that the average of your 100 samples is greater than, let's say, 100? And then you will need to use the normal distribution here to facilitate the calculation. Yeah, but here when you need to perform the calculation, you will need to know the mu and the sigma square. So you as a researcher will need to provide those numbers or come up with those numbers to calculating your downstream analysis. Yeah. And to know what exactly or the samples for those or the number for those mu and the variance, that is called parameter estimation. So the idea here is that the first step is to collect data. Okay. Second, make assumption of their distribution. So for example, you can assume that it's normal. Then you will need to perform something called maximum. So we are not there yet, but so I'm just writing down some keywords for related to your question. So you will need to do something called maximum likelihood estimation to get your parameter for the model that you assume. So in this case, you might assume that this is normal. Then you will need to calculate from the data what is your mu and sigma square. Once you know the mu and sigma square, and then for some downstream analysis. Something like that. So that will be the procedure. And what we have done, so what people can do here is collecting data. We can just collecting data. We can easily make assumption based on all the distribution that we know of. We can make assumption that the data follow exponential, normal, gamma, or there are tons of other distribution that you can impose on your data set. So that's the model. Okay. And then the maximum likelihood estimation. This is a very mathematical intensive methods. For example, training neural network is essentially maximum likelihood estimation. So you will need to perform a very intense mathematical calculation to do this procedure to get the parameter. Once you have the parameter, you can perform downstream analysis. So for example, in ChatGPT, people from the OpenAI do first collecting data. So that is all the text on the internet. So that's what they do on collecting data. Next, they make assumption on the model. The model that they assume is the GPT, right? Generative Pre-trained Transformer. That's a decoder, something that we also mentioned last time. So that's the model that they make the assumption. So that's stage 2. Stage 3 is maximum likelihood estimation. That is the training the neural network part. The 4 is the result, is the utility that we use ChatGPT. When we ask questions, we get feedback. So that's the 4. Okay. But so that is the ChatGPT case. But in our case, we will also need to do the same to answer the question like what is the average of the patient some vitals greater or lower than that. So to answer that kind of question, we need to go through all these procedures. And the most important part is the step 3, which is highly or very mathematically intensive. You will need lots of mathematical or optimization technique to perform that. And even for training neural network, that is even difficult for step 3. Yeah. I hope that answered your question.
Well, this was very informative. It didn't. Ultimately, my question was just around problem-solving logic of the example that you were.
Oh, okay. Yeah. So
You pulled the parameters from the X sum case.
You learn from them. You learn from your data.
So we're supposed to having just been taught this, know that we can just pull that.
Yeah, because right now we are in the state that they are provided, or you are like a it's like an oracle, like you know everything. Yeah, but in practice you don't know. Yeah, you never know. Then you will need to do the stage 3 to learn the parameter. Yeah. So all these are just textbook examples. You assume you know, but that's not how the real world behaves. Yeah. So if you look at all the textbook, it will say, okay, so the average of some measurement is like a 100, and then standard deviation of 5, and then calculate this and that. But that's just textbook. It's well, not useless, but it's a practice of doing problem like this. Yeah. Yeah. But in practice, when you're collecting data, you need to know, you need to estimate those parameters. Here, all these are just textbook example. Okay. Any other question or comments?
If you were to actually carry out the probability,
Hmm?
if you were to actually carry out the probability of that new parameters up there, would you have to do like the whole like integral and whatnot?
You mean how to estimate them? Or what was your question?
Because you have written there probability of x bar
Yeah.
following something something.
Mm-hmm.
That's the case where we
That's the case where you need to calculate an integral,
Yeah.
the area under the curve. Yeah.
Okay. And wherever the sigma was, that's you replace it with the sigma squared over n.
Yes, that's your new variance.
Okay.
Yeah. Okay. Next, let's also consider some applications. So we are done with the moment function. Let's just consider some examples or applications for what we can calculating the probability of something. Okay, so first of all, let's consider that we have a coin. One coin. Okay, so this coin is biased. So when we flip a coin, you can have two results. One is landing on head, the other one is landing on tail. And this coin is biased, so let's assign. So this is the part where we assign where we know the probability. So we assign, let's say, the head with a probability of 0.3, and then the probability of the tail is just 1 minus that. Because when you flip a coin, you can either get a head or tail, and here is the number that we provided. But in practice, if you want to know the probability of a coin landing on head and tail, you need to keep flipping the coin, collecting data, calculating what is the probability of head and tail. Okay, but here we just put down is 0.3 and 0.7. Okay, so when we flip a coin, we will have the following results. So we will have the probability of head and tail that is equal to 0.3, and the tail is probability equal to 0.7. Okay, so we can come up with this kind of figures. And then in what we define the probability or the random variables, we usually use numerical values to representing the state of head or tail. So instead of rating as head and tail, let's give it numeric outcomes. So we can write x is equal to 1. That is the case where it landing on head. And then x equal to 0. So like a binary case, x equal to 0, that is say we do not have one head. So we have 0 head, then x equal to 0. So we can then further rewriting or to replace the labels for this figure. This is x equal to 1 with a probability of 1.3. So we have, when we flip a coin, we are landing on one head. And when we flip a coin resulting in 0 head, that is saying we have a tail. We flip a coin and then resulting on a tail. Okay, so that is the case for one coin. Now let's take a look at the behavior of two coins. So when we flip two coins, then we will have the following outcomes. We will have head and head. We could also have head and tail. So the first coin landing on head and the second coin landing on tail. But we can also have the other order where we have the first coin landing on tail and the second coin landing on head. And then the last outcome will be two tails when we're flipping two coins. Okay, so that would be the result. And now also replacing the result from the latter with the numerical values. So the first case is that when we're landing on two heads, that is saying that x is equal to 2. we have seen two occurrence of the hat shown coming up from the result. So we're using numeric value, the random variable, that equal to a numeric value to representing the state. So we have two hat observed, so x equal to 2. And then for the two case in the middle, they belongs to the case where you have one hat, okay? So x equal to 1 for the two case in the middle. And then for the last one, we don't have any hat, so this is saying we observe 0 hat. That is saying that we observe two tails. So we write x equal to 0 to representing as a numerical representation for that particular outcomes. Okay. Now, okay, so maybe let me also put the value. This is 0.3, this is 0.7. Okay, so now let's calculating the probability for these two cases, for the case with the 2 coins. Okay, so we know that the probability of 1 coin landing on hat is equal to 0.3. Then for the probability that the x equal to 2, which is that we observe 2 hat, this is equal to 0.3 multiplied by 0.3 equal to 0.09. Okay, that is for the x equal to 2 case. And then for the 2 case in the middle, we will have one hat 0.3 multiply by one tail, that is equal to 0.21. But is that the probability for observing, or that we can assign to the case where x equal to 1 or not? That should not be the case, right? Because that is only for one result, one of the outcomes here. You could also have the other outcomes in the different order. You can have the 0.7 by landing on tail on the first case multiplied by 0.3. So that is saying you will have 2 times the 0.21. You will have the 0.42. This particular numeric probability assigning to the outcome of the x equal to 1. Okay, so for x equal to 1, it will has the numeric value for 0.42 for this particular outcomes. And finally, for the last one, you will have 0.3 multiplied by 0.3 equal to 0.49. Okay, so with the 2 coins, we will have 4 different outcomes. And then, but we only have 3 values that we can assign to the outcomes, which is x equal to 2, that means there are 2 hats. X equal to 1, representing the case where we have 1 hat. X equal to 0, representing the case where we have 0 hat. Okay, and then we also calculate the probability for each of the random variable x. We can also make a figure like this. Okay, so x equal to 0, x equal to 1, x equal to 2. We will have this one, 0.09, x equal to 1, about 0.42, x equal to maybe here is 0.42. Maybe the scale is not too good, but we can this is 0.42, and then we will also have the case of 0.49. Okay, so what we have done here is that we see the actual outcome, but we rewrite as using the number to representing the random state, the outcome. And then we can also have the following figures. Okay, so let's.
I think your x, the x equals 0 and x equals 2 is
Do I have the different order? Okay, yeah, thanks. So then this is 2, that's 1, and that's 0. Thanks. Yeah. Then, yeah, but it would be better that you put the 0 on the left, but since I already have the figure, so maybe you can just do a mirror reflection for your figure. It would be good to put the zeros on the left hand side. Yeah. Is that what you were saying? Yeah, thanks. Yeah. Okay, so let's do one more example for the 3 coin case, and then we will make some comments on what we're doing here. Okay, so 3 coins. So again, we can have the 3 head, also the 3 tails. Now let's also list the other cases. We can have the first of 2 are head, and then the head, tail, and head, and then the tail, and then head and head. And then we can also have 1 head and then 2 tails. Okay, so here for the 3 coins cases, we have these 8 particular outcomes. But then they can also group in the following categories in terms of the random variable. So again, let X denote the random variable as the number of head observed. Then we will also have the case for X equal to 0, X equal to 1, and X equal to 2, and then X equal to 3. Okay, so when we flip 8 coins, we can have the 8 different result in terms of the coin. But when we're talking about the random variables, we would define X as the number of head observed. Then we can see that the X can equal to each of the 4 different categories. Okay, so now we can also calculate the probability for these cases. So for 0 head, that's just the case for 3 tails. So that is the 0.7 raised to the power of 3. Maybe I'll just write down 0.7 raised to the power of 3. Okay, and then for the 1 tail, 1 head cases, okay, so maybe let's start with the X equal to 3. That is equal to 0.3 raised to the power of 3. Okay, so that's for the 3 head cases. And now let's take a look at the head equal to 1. So we'll have 0.3 raised to the power of 1 multiplied by 0.7 raised to the power of 2. But that is just one occasion or one particular outcomes from your table of 8 different ways here. So we also need to multiply by how many ways that you have in your outcome in terms of the coins. So in our case, for 1 head, we can see that the right column where we have 3 occasions, so we will need to multiply by 3. And that is the total probability that we can assign to the random variables that X equal to 1. And then similarly, for the X equal to 2, you will have 0.3 raised to the power of 2. You have 2 head multiplied by the probability of tail. And by looking at the table, you also have 3 occasions, and then you will need to multiply by 3. Okay, and then here, when you sum them together, so you can use a calculator and calculate them, their sum is equal to 1. So here we have defined a particular random variable, and more specifically, a distribution to describe the number of head, this random behavior in that particular context, by flipping 3 coins. Okay, so what we have done here is essentially building a distributions. we have building a distribution. In this case, it's the binomial distribution. Okay, so here you can see that first of all, we need to account for the number of head and tail that we get in each occasion. Okay, so we can write the probability of x equal to k. So in this case, in the 3 coin cases, k can be equal to 0, 1, 2, and 3. Okay, and then we have the part where we calculating the probability of each coin. So for example, 0.3 equal raised to the power of k, where k is representing the number of head that we observe. And now, because we have 4 possible outcomes, so here let's define the total number of the outcome, the maximum outcome that you can get for the axis will be all the way up to 3 for a 3 coins. So we'll have 0.7 for 3 minus a k. Okay, so this particular product here can handle when we calculate the probability for the resulting head and tail for each of the coin. But we notice that we also need an extra factor to account on how many occasions that we have 2 coins and 2 head and 1 tail, and how many occasions for 2 tails and 1 head. Okay, so then we need to have another mechanism to construct or to describe this random behavior. And this one can be done by the binomial coefficient. So here we have the 3, so we write it as 3 choose k. Okay, and this is essentially how we build a binomial distribution by using a more specific concrete examples. Okay, so here you can see that the binomial coefficient is a way to handle or to count how many occasions that we can get for the by throwing 3 coins and then getting different numbers of the number of head and tails. So here, when we're flipping 3 coins, we are supposed to have 8 outcomes. But when we talking about the random variables, we can see that there are only 4 different cases that we should consider. And then by doing this procedure from here, you can see that by describing this kind of random behavior, by counting how many heads, we have built a distribution, which is the binomial. Yeah, question?
Can you explain what the 3?
Yeah, I'm going to talk about now. Yeah, so essentially the 3 choose k here is the way to handle the counting part, where you have the when you have n different objects and then you want to choose k of them. So in our case, the n is equal to 3. So we have 3 different outcomes in our random variable. X equal to 0, x can go all the way up to 3, because we have 3 outcomes. So x equal to 0, 1, 2, and 3. So the maximum can be 3. And k is that the outcomes that we can get. So k can range from 0, 1, 2, and 3. And then this part will have this, so and then this binomial coefficient will handle this part. So the formula exactly is n factorial and then k factorial n minus k factorial. Okay. So now if you plug in, so now let's revisit this example here. So this is saying we have 3 different outcomes. We want to choose 0. If we plug in the formula, you have 3 factorial and then 3 factorial and then 3 0 factorial, and then 3 minus a 3 factorial, you get exactly 1. So by using this binomial coefficient, you can handle the counting part. And then when you plug in the formula, you can see that there's only one occurrence for the case when out of the 3 outcomes for your random variables, you can get, and there's only one outcome that you can get 0 hat. So this part will handle, so this counting procedure here will handle the part when you, how to reduce your 8 outcomes from the head and tails into the random variable where we consider the number of head. Yeah.
Can it be 3 minus 0 if it's n minus 4?
What is that? Sorry, what was that?
You said if k is 0 and n is 3, should it be 3 minus 0 on the top of the denominator?
Oh, thanks. Yes. Perfect. Yeah. Otherwise, it's 0 and 0. Yes. Thanks. Yeah. So this is just a mechanism to handle, to how to kind of like a counting from 8 different outcomes in terms of the coin, head and tails, and then reduce or collapse them into the 4 outcomes for our random variables. So our random variable here is only interested in how many head that we observe in flipping 3 coins. And then that particular binomial coefficient will handle that part by collapsing some of the outcomes. So for example, here we have 3 here, and then collapse into equal to 1 case. And then multiplying by the corresponding probability, then we will have the probability mass function to describe the behavior that when we're flipping 3 coins, how many outcomes, how many heads that we can get. And yeah. So similarly, by plugging the formula, here we will have 3 choose 3. You will have 3 factorial, and then 3 minus 3 factorial. That will also give you a 1. Okay. And now let's also apply this formula for the x equal to 1 case. We have the 3 choose 1 is equal to 3 factorial, 1 factorial, 3 minus a 1 factorial. And this is equal to, this should be equal to 3. Okay. And then similarly for 3 choose 2, so you have the 3 different outcomes, and then you want to choose the case where you have 2 heads. And then when you plug in the formula, you will also have 2 factorial, 3 minus a 2 factorial. This will also be equal to 3. Okay, so the leading binomial coefficient in the front will handle from, or will collapse the counting part from 8 different outcomes into how many heads that we can observe. And then this will give us the binomial distribution. Okay. And this formula, as we have shown from the counting, and also by building this table, will give us the probability that we'll get flipping 3 coins and then get exactly 0 head, getting 1 head, 2 head, getting 3 heads. And this formula will give you the probability of exactly k, the number of k as the head that you will observe, and then out of 3 coins. And this distribution will describe this behavior here. Okay, so we have built the binomial distribution from scratch. Okay, but now by looking at this formula, there's one problem here, is that if I ask you a question, so what happens if there are 10,000 coins, and then each landing on head with probability 0.003. Okay, so now if I want to calculate, or if someone asking you that now I have 10,000 coins, each of them has a probability, landing on head has a probability of 0.0003, and what is the probability that we observe exactly 2 head. Okay. So here we started by building a distribution, which is the binomial distribution. So we build it from scratch by seeing the coin flip examples. And then, so that is saying each different trials, you will have a probability of success or failure. So in our case, the success is landing on head, and the failure is landing on tail. Okay, so we can use this kind of things, or the formula that we just built up, that we construct here, to describe this kind of random behavior. But sometimes when your number of trials, so in our case, the number of coins, can be very large, and then the probability of that success, or in our case, landing on head, can be very small. So if you want to use the distribution, or the formula that we just derived, that we invented here to answer this kind of question, so now let's plug in the formula again. So we are interested in x equal to 2. But then by plugging in the formula that we invented here, which is the binomial distribution, you will need to calculate 10,000 choosing the 2 to handle the part where you collapse 100 coins. So you will need to write down all the possible combinations for all the heads and tails, and then doing the counting part, and then to get the probability, and then to answer this question. So you will have the 10,000 choose 2 multiply by 0.003 raised to the power of 2 times, multiply by 1 minus 0.003. So 1 minus 0.0003 is the probability of landing on tail for each case. And then you have 9,098 of this occasion to calculate for the probability that a coin or a trial that is failure, or a coin that is landing on tail. Okay, so if you have this kind of question, then you will need to use the binomial distribution, this particular formula, to answer the question. However, back in days, again, calculating the product of a small number, for example, the 0.003 raised to the power of 2, or that number raised to the power of like thousands, and also you need to handle the binomial coefficient, the counting part, to handle the listing all the combinations here, is very difficult and not feasible back in days. Then how do people solve or to approximate this probability here? And then people invented the Poisson distribution. Okay, so the idea that people invented the Poisson distribution to handle this kind of problem is that they started with the expectation of a binomial distribution. So if you use the moment function to calculating the the first moment, or which is the expectation of binomial distribution, I think this is also the result that you get from midterm, is n multiplied by p. So in our case, we have 10,000 coins. Each of them has a probability landing on head equal to 0.0003, and that is saying, on average, you are expected to get 3 heads in this occasion. But that is the expectation of a binomial distribution. Okay. So instead of calculating the probability that could end up into a floating point issue, which is saying that you have a large product of a small value or a large product of a very large values that you cannot calculate it manually, or even in computer, you cannot store a number that's small or store a number that is very large. So to work around with that particular issue, people come up with the idea of using a Poisson distribution to handle this case. And the idea is that they will starting from the expected value from the binomial distribution to work around for this problem. Okay, so now we know that the expected value for the coin is equal to, for this particular case, will be equal to 3, and we are still interested in the probability that we observe 2 heads in that case. Then here we can use the Poisson distribution to approximate the probability from a binomial distribution process, but that is not able to calculate an exact number. Okay, so now we can use the Poisson distribution. And then the formula for the Poisson distribution is that the e raised to the power of negative lambda. So here, the lambda, we can use the expected value from the binomial process to plug into our Poisson distribution. And the underlying idea here is that when we use the moment function, when we're calculating the Poisson distribution in the early lecture, we mentioned that the expectation for a Poisson distribution is exactly the parameter. So we already proved, or we already showed that. So here we can use, or back in days, people can use the expected value that they get from the binomial process, the negative lambda, and here we replace the lambda by 3 here by using the expected value. And that is the reason is that the expected value for Poisson that we have proved is that it's the parameter itself. So we can bring in the expected value to replace the parameter lambda for a Poisson distribution. Okay, we'll have lambda raised to the power of x. In our case, we are interested in 2 coins, and then x factorial, that is 2 factorial. Okay, so now we can see that. So if we're starting from the binomial process or the binomial distribution, when there are cases when we have very large number of coins and low probability that we cannot handle manually, or even nowadays computer cannot handle. So people then invented the Poisson distribution, and by borrowing all the moments that we calculated before to work around this problem. And now if we plug in this one with the 3 with the expected value equal to 3, and then plug into a Poisson distribution, and if you're calculating that, you will get this one equal to 0.2240418. Okay, and that is the probability that you can calculate, that you can relatively easy to calculate from a Poisson distribution. And here, let me also provide the probability from the binomial distribution. So if you're calculating this from the binomial distribution, this is about 0.224053. So this is from the binomial distribution. And this is from the Poisson distribution. And this is an approximation, or a way to work around from the floating point issue that we cannot handle the product multiple products of a very small values and multiple products of very large values. So we can use a Poisson distribution to approximate the actual number the actual probability that we are interested in. So that's that. Okay, so after people developing the Poisson distribution, so let's take a I think there are 5 more minutes. Maybe I will stop here and then are you guys interested in maybe a quick like a side note since we have 5 more minutes? So this is not course related. Have you guys heard of are you guys familiar, have you heard of neural network before? Have you guys heard of recurrent neural network? So recurrent neural network is a type of neural network that handle time series or sequence data. The thing is that when they want to handle time series data, they come out with this recurrent neural network. But there's one issue related to this neural network, which is very similar to this binomial coefficient thing, is that when you're implementing recurrent neural network, you need to, as it names, you need to recurrently making prediction from the neural network. And this recursion here is performed by taking the products. And also when you estimating the parameter of the neural network, you also need to do it recursively. But when things happen in a recursive way, lots of the floating point issue will show up. So when you're calculating the gradient, you also need to calculating the product of a very small number. And when the gradient is very large, you also need to calculating the gradient of the product of a very large number. So back then, although people have proposed a recurrent neural network in the machine learning communities, but rarely people can train a very good recurrent neural network to perform a very good like a forecasting task. So how people solve this issue is that they invented another thing called the LSTM. Have you guys heard of that? LSTM, which stands for long of the short-term memories. So their idea is that instead of doing the products of lots of small values or large values, like the thing we encountered here when we invented the binomial distribution, is that they replace the product by sum. Okay, so if you have a lot of small values, then you can sum them up, then you will not have the floating issues. But the LSTM can solve the problem for the recurrent neural network called gradient vanishing. But it cannot solve the problem that is called gradient explosion, which is the product of multiple products of large numbers. So right now, the LSTM can still not solve the problem. But what they did is that when they perform gradient descent, that they need a learning rate. So in computer, you just put a very, very small learning rate in the computer, and then to let the LSTM trainable. Okay, so this is just a side note of some history of the neural network, where since we have encountered this issue here, and this issue is also happening in the neural network community, and then people come up with the LSTM to solve the gradient vanishing problem. But the gradient explosion problem is still there, but people just use a very small value, small learning rate to handle that. Okay, but it's just a side note that derived from the problem that we encountered here. Okay, yeah, that's it.
I'm not sure if I missed it when you're talking about in the beginning of class, but we got our midterm grades back.